The question we have here is how many stairs we have to climb to burn the calories of eating one of these. And when you find out what that number is, you're probably not going to eat yours. Let's assume the stairs are normal stairs with the height 20 centimeters, which means 0.2 meters. So the height is 0.2 meters. How many of these stairs you have to walk to burn the calories of one of these Thin Mint? Again, we just Googled that. First I was about to do this candy bar, but we don't want to discourage you completely. This is 100 calories on it. You can see it here. It's a normal candy bar. It's supposed to be a healthy one. But we'll take the Thin Mint. It says it has 25 calorie, big C. Well, here's the news. One big C, one capital C, is equal to 1,000 calorie. 1,000 of them. And here's the other bad news. One of these calories, the little c, Cal, is equal to 4,186 joules. So when you look at that Thin Mint, which has 25 calorie, when you eat it, capital C here, that's over 1. To change calorie to cal, 1 cal is 1,000 cal. C's are gone. And now I need to go from calories to joules. 4,186 joules. So we do quick math on that. $25 times 1,000 times 4,186. Ready for this number? That has 1, 0, 4, 6, 5, and 4 zeros at the end. Joules. That's what a 25 calorie is. And the question is, how many steps you have to climb to burn that? When you're climbing, you're going uphill, that's potential energy. Calories, energy. Potential energy is mass times gravity times height. Let's take an average person, I don't know. What do you want to use for how many pounds? 180 pound person? So what's 180 pounds divided by 2.2 kilogram? 2.2, that's 81, almost 82 kilogram. Let's say the mass is 82 kilogram, which is approximately 180 pounds. Person. How many stairs that person has to climb to burn those calories? Well, potential energy is equal to mass, the mass which is 82, gravity 9.8, times the height which is h. And you want these numbers to equal to each other. So set the two numbers equal to each other. Can we get what h is? Oh, 104,65,00,00 divided by 82 divided by 9.8. Oh, God help us. Oh, God help us. You don't want to know what that number is. 25,000. Is that number correct there? Because it looks like lots of steps here. 25,000 times 4,186. 10,465,0000. Yep. So divide that by 82 divided by 9.8. I'm getting a huge number. I'm getting 130,000. Is that what you got? Can't be. That's a huge number. There's no way you're going to climb that many steps. 20.
No, it should be 104,650 because that 4186 is 4.186.
Yeah, I'm sorry. Yeah, per thousand. 4.16. Yep. One big calorie. One capital C is 4,186 joules. You're right. Yep. So 1 calorie, small one, 4.186. So move the decimal point 3 places. So we lose three zeros here. I'm saying you got to climb a lot of steps here. Yep. So let's try that. 10,4650 divided by 82 divided by 9.8. It is 130 meters you got to climb. Well, each step is 0.2. So if you divide it by 0.2, we're going to climb, guess how many steps? 651 steps to eat that little Thin Mint. Where is it? Where did it go? Did I eat it again? No, right there. Just to eat one of these, I got to climb 651 steps there, just for that little stupid calorie, that mint. So working out's not worth it. There's no one on earth I'm going to work out that much in the gym today. Walk that many steps. So one of these, Jonathan, you work out, you eat this. Since you work out all the time, that's yours. I don't want it now. Imagine if I took this candy bar, that's 100. It'll be 4 times that number. 2,500 stairs I gotta climb just to eat this candy bar. Who wants to walk 2,500? You can have this. Anyone wants it? They're all right here. Oh. So we're going to talk about heat. Yeah, 1 little calorie here equal 4.186. 1 capital C is 4,186 joules. Because one of these C is 1,000 of them. So when you look at these numbers, it says, drink this soda, has 320 calories on that soda. That's 320 of these capital C. Which means multiply it by that, that's how many joules you have to burn just to get rid of that soda. Yeah, I could have went directly from this. Instead of going to small k to this, I could have went from this to this. We're going to define something here called Q, which is heat. And heat is really the energy transferred. Due to temperature difference. When we have a difference in the temperature. If there is no difference in temperature, the heat transfer is 0. And Q can either be gained or lost. And before we get to that, let's talk about something called specific heat. So Q can be either gained or lost. How do you gain heat? When do you gain heat? When you take a cold object and you put them in warm container or warm solution. When you put ice, for example, you put ice in coffee or tea. You want to make an iced tea. You make a hot tea, you put ice in it. Ice will gain some heat because it's cold, it's going to take some of the heat. On the other hand here, Q lost the tea, so the ice here, the ice will gain the heat. The same example, if I take ice and tea here, hot tea, the tea here will lose some heat because the tea is hot, ice is cold, the tea temperature will drop down, so we'll lose some heat there. That's the heat loss, that's the heat gain. So heat could be either gained or lost. When you go from cold to warm, so cold to warm, you're gaining heat. When you go from warm to cold, you're losing heat. The heat at the tea here is warm, it's hot. You put the ice in it, the tea will get colder. You go from warm or hot to cold, that's Q lost. This is Q gained. So let's talk about specific heat. We need to know how much heat is being lost. Well, it depends on the material of that object. What are we putting there? For example, if you put ice in tea or in hot water, the water will get cold. Now, if I take a copper, and let's say I have some of these copper balls, and I put them in the freezer with the ices, they have the same temperature. So when they come out of the freezer, they have the same temperature as ice. And I put those copper balls in water. So in one container, I have ice cubes. In the other container, I'm putting these copper balls, that's 3D supposed to be, I'm putting these copper balls with the same mass, same temperature. In the next one, I'm going to put steel balls with the same mass, same temperature. Is the temperature of the water or the tea here, is it going to be the same? The answer is no. And the reason for that is something called specific heat or heat capacity. Let's talk about that. So let me define heat capacity. And let's give it the letter C. Heat capacity. By the way, that's one of the reasons we don't like to use capital C for calorie. Because if I put C, you might think, is that heat capacity or calories? So a lot of these problems you see, we write CAL for calorie, the smaller c. So heat capacity C. The heat capacity can be found. We can actually go to the lab and do that. Calculate with the heat capacity. And that is how much heat was added during a specific time. the amount of heat per time. Oh, change in temperature, I'm sorry, not time, change in temperature. So here we go. We define heat capacity. I can go to the lab. It says add the heat Q to a given object and its temperature increases by delta T. So if I know how much heat I'm adding, and I know what the change in temperature is, you divide the two numbers, that's your heat capacity. We'll tell you how we calculate how much heat was added there in a few minutes. So if you look at that equation mathematically, it says Q equals C times delta T, change in temperature. So what is heat capacity? What is C? We define C, really, heat capacity. That's how we calculate it. But we define heat capacity as the amount of heat needed to change the temperature by 1 degree. How much heat is required to change the temperature by 1 degree? That's what heat capacity is. And it changes from object to object. So for example, if you take a bucket of water here, and you can add heat to it, and you watch the temperature here. Once the temperature increased by 1 degree and calculate the heat here, now we're going to worry about this for 1 kilogram. So if it's more than 1 kilogram, we're going to deal with that. And we multiply them, and we get actually what C is. C is, and remember, the temperature is 1 degree if you look at it, so the change in temperature will be 1. So heat capacity will be C equals Q divided by 1. You change it by 1 degree, which means C equals to Q, the amount of heat needed to change the temperature by 1 degree. How much heat was given is added there to change that temperature of that container by 1 degree. Now the question becomes, well, if I have a cup like this one, it's not really much in it, and I want to change the temperature of that by 1 degree. Would that require the same amount of heat that if I want to heat my pool by 1 degree will be the same amount? There's no way. To heat your pool by 1 degree, that's a massive amount of water. That requires actually a lot more heat than to change the temperature of this by 1 degree. So to change the temperature by 1 degree depends also on the amount that you're trying to change. Is it 1 gram, 2 grams, 1 kilogram, 1,000 kilogram, a swimming pool? What is it? Now for water, by the way, just for the record, C for water is equal to 4,186 joules. What does that mean? Heat capacity is the amount of heat needed to change the temperature of 1 kilogram. It's really 1 kilogram. temperature, I should add here, of 1 kg, 1 kilogram, by 1 degree. So for water, the heat capacity is 4,186 joules. We will need 4,186 joules to raise the temperature of 1 kilogram of 1 kilogram of water by 1 degree. That's how much heat we're going to need. 1 kilogram of water by 1 degree. We need that much heat. Now copper is different. Ice is different. It changes from object to object there, substance to substance. So for example, here we go, just to give you an idea, water is 4,186 joules per kilogram per 1 degree, Kelvin. Changing in 1 Kelvin degree is the same as 1 Celsius degree. The change is the same. Ice is a little bit less, 2090. Steam, 2010. Air, 1004. Aluminum, 900. Glass, silicon, steel, 448. So it doesn't take much to heat steel. Silver, 234. Gold, 129. Water is one of the worst one. It takes so much heat to raise the temperature by 1. On the other hand, gold, 129. If you take 1 kilogram of water to raise the temperature is 4,186. How many kilograms of gold that you'll need to raise the temperature by the same amount? Where's my calculator? I'll take 4,186 divided by 129. That's the same as raising the temperature of 32 kilograms, almost 32.5 kilograms of gold by 1 degree. The amount of heat required to change the temperature of water, 1 kilogram of water, by 1 degree is equal to the same amount of heat required to change 32.5 kilograms of gold by 1 degree. Doesn't take much for gold to heat. Same thing with steel. Same thing with glass, aluminum. Air. Yeah. So the equation really for Q here, how much heat is required, Q, because it depends on, we said C times, what was a few minutes ago, I said what? Q equals C times delta T. If you only have 1 kilogram. What happens if you have more than 1 kilogram? So the amount of heat required, it's the mass times C times delta T. Okay, let's see what will happen here. I have a container, styrofoam container. We'll use styrofoam container here. You know what? Let's not even make it styrofoam. Let's make it aluminum. Let's make it more fun. And do aluminum. We have aluminum container. The mass of the aluminum, that container, is 210 grams. It has water in it. There it goes. It's a cup here. The mass of the water equals 550 grams. And they've been sitting there for a while, so the container and the water have the same temperature. The temperature of the water is 32 degrees Celsius. The temperature of that aluminum is also 32 Celsius, because they've been sitting there for a while. Notice we use these styrofoam cups here because they're good insulators. As the air goes around this, it's going to cool the coffee quicker, actually. Now with this, styrofoam, actually the air is not really that much of a factor from the side and the bottom. Only the top, because it's open. But with the aluminum, as the air goes around the aluminum, cools, it warms it up there, and that hot drink that you have there is no longer hot, or the cold drink, if you put ice in it, you come back half an hour later, the ice is gone. It melted, the surrounding temperature. So what happens here? We decided to add, what should we put in it? We're going to take here, ice. You want to put ice in it? Let's take a block of ice and throw it in. We took an ice cube, and here's my ice cube. I shouldn't use ice, not yet, because that's change of phase. Let me be patient on that. Instead of ice, let's use gold. This is gold. I got a piece of gold. The mass of the gold here is 1 kilogram. Well, that's a lot of gold. I won't be doing that experiment. I'll be rich. I'll be running around. So the mass of gold is 0.1 kilogram. Still a lot of gold. And the gold happens to be the temperature of the gold initially. Pick a number. You want it hot, cold, whatever you want it to be. What do you want the gold to be? 100 degrees Celsius? So I heated this gold and I dropped it in that container, in that water there. I should use like aluminum, like blacksmith, when they make a design, they heat the piece of metal, they bang on it, then they put it in the bucket of water. I've seen them do that. And the question, what's the final temperature? What's T final? You can drop that gold and let it sit for a few minutes, and because we have a difference in temperature, now what will happen is heat is actually going to leave that gold and go to the water in the aluminum container. We have to assume we don't lose any heat to the air, the surrounding air, the open container there, so we have conservation of energy. Q lost plus Q gained has to equal to 0 when you add them. If you take the amount of heat that was lost, which means from the gold gave away, and add it to the amount of heat that was gained by these two, the result should be 0. I didn't say equal to each other because one is going to be positive, one is negative. So Q gained, that's positive, Q lost is negative. So they'll never be equal to each other. They'll be equal to each other in absolute value. But Q gain is positive, Q lost is negative. So positive 50, the other one is negative 50. So when you add them, the result is 0. So let's see, who's going to lose heat? We know that's the gold because it's warm. And who's going to gain heat? We know it's the water plus what? The aluminum. So this is the gain, that's the lost. And in Q for any one of them, I'm going to be using, it's the mass times C times delta T, change in temperature. So let's talk about the gold. What was the mass? 0.1. And what was C? That's the specific heat. I have to go to that chart. The specific heat. That's this chart. We'll look at it quickly. For gold, 129. Can you see it? For aluminum is what? 900. And for water is what? 4186. See the numbers? So these are the numbers I'm going to be using. That's C for each one of them. So for gold, the mass times C times delta T. C is 129, the specific heat, times delta T, the change in temperature. Well, my initial temperature, change in temperature is final minus the initial. Final temperature, I have no clue. I'll call T final. The initial temperature of gold was what? 100. And notice we know the temperature is going to be below 100. So that's why that number will be negative. Let's see who gained. As this is the lost here. The gained, let's start with the water. The water, the mass of it, which is what? 0.550 kilogram, times C for water, 4,186, times the change in temperature, final minus the initial. T final minus the initial, which is 32. Add to it the aluminum. The mass 0.210. C for aluminum, we say, was it 900 for aluminum? 900 final minus the initial. All of this has to equal to 0. Now you just got to do the math. 12.9 TF minus 1290 plus, let's see what that number here, 0.550 times 4186 minus 73673.6 plus 0.2 times 900 times TF, that's 189 TF, minus 6048 is equal to 0. I can take all the ones with TF, put them together, get one number out of them. And I can take these numbers, put them together, and get one number out of them. $81011.6 with the minus sign, and the other one 12.9 plus 2302.3 plus the 189, 2504.2 TF, 2504.2 TF equals 81011.6. What's the final temperature is going to be? It better be more than 32. How much? I don't know. 32.4 degrees. Only raise the temperature by 0.4 degree. Again, gold doesn't have that much heat in it. 129 for every kilogram. To change the temperature by 1 degree, you only have to give 100. Like if that was 1 kilogram, to change the temperature by 1 degree, you have to give 129 calories, 129 joules there. That's not, joules, not calories. That's how much heat is required. So there's really not much heat in gold there. This is 0.1 of a kilogram. So you're not getting a lot there. Let me try another one. Here's my plan was for the lab today. I'll go over the math, and if it's late by the time we figure it, we'll save it, and that'll be the one we run tomorrow. I'm going to take an aluminum container, just like we just talked about it here. Our aluminum container is surrounded by wood. Wood is a good insulator, just like styrofoam is a good insulator. Has a top to it, cover it. But inside that, we have an aluminum container. We'll take the mass of it. Let's say the mass equals, I don't know, 0.2 kilogram. I'm going to open the faucet. We're going to weigh it, so that's 0.2 kilogram. Then I'm going to open the faucet, pour some water on that. There's the water. I have no idea how much water you're going to have. Then we'll weigh the whole thing. And let's say it's 0.5 kilogram right now with the water in it. That tells me the water, the mass of the water, is going to be 0.5 minus the 0.2, which is what? 0.3 kilogram. And my plan was to cover it, put the cover on, stick the thermometer and wait for a few minutes. Now, the water probably going to be colder than the room temperature. So if you wait for a few minutes, you'll see the thermometer. This is the thermometer coming down here. You see the temperature of the water actually start to drop because that water is going to be colder than that. So some of the heat will transfer from the container to that. But you'll see the water comes down, finally it's going to stop. The temperature is going to be right there. And that's the temperature of the water and the aluminum container. We reach equilibrium, thermal equilibrium. So we look at that temperature, and let's say the temperature equals, I don't know, what's the room temperature in Fahrenheit? 70? That's about, let's say, 20 degrees Celsius. Now, I'm going to take different bowls for each one of you. We'll get a different bowl, and I'm going to heat them. Now, I can't put really these metal bowls in the microwave, so what I do, I will take water here and boil it in the microwave. I get some water, boiling water, till it's boiling. And once it boils, I'll take all these bowls and I'll drop them in. Different kind of bowls. Some are steel, some are copper, some are aluminum, some are glass, different kind. When you boil water, the temperature is roughly 100 degrees Celsius. So after it boils, I'll drop the bowls in it and wait a few minutes till these bowls reach the same temperature. So when I take them out of this, when I take the bowls out of this and put them in your container, they're probably somewhere around 90 degrees. So each one of you is going to have a different bowl in their container. So I'm going to drop a bowl here. We'll know the mass of it. We'll weigh them after too or before. We'll know the mass. So let's say the mass of that item I'm putting there, the mass equals, I don't know, 0.1 kilogram. And you have no idea what you have with you. You don't know if it's copper. You don't know if it's steel. You don't know if it's aluminum. Aluminum easy to spot by the color of it and slide there. But it could be silver, could be copper. I doubt it would be silver because I would keep them. It could be iron, gold, lead, could be anything. And the question is, can you tell me what I gave you? Can you tell me what that is? And the only way to figure what that is by finding what C is. So your job becomes, can you find what C for that bowl is? The specific heat. And the only way you can do that, if you wait a few minutes, because this is going to be hot, the temperature actually of the water is going to rise. And when you look at the final temperature, that's the initial temperature, we'll use O. Now the final temperature of everything, that means the bowl, the water, the aluminum, let's say it went from 20 to 30. So I started with 20 degrees Celsius, now it's 30 degrees Celsius. Can I tell you what that item is? Can I find what C is? I should be able. And that is, I will say Q lost plus Q gain should equal to 0. The amount of heat that's lost, add to it the amount of heat that's gained should be 0. The reason again, this will be negative 50, that'll be a plus 50. This will be negative 1,000, that'll be a plus 1,000. Conservation of energy. But the loss will be negative, the positive, the gain will be positive. And you can't say Q loss equals Q gain. Negative doesn't equal to positive. So I say, who's going to lose heat? That object. I'm dropping there. Which is the mass of the object. I use O for object. Times C for the object. Times the change in temperature. Who's going to gain heat? The aluminum container, the mass of the aluminum. C of the aluminum, change in temperature. And also the water. Now the object I dropped in has a mass of 0.1. I don't know what C for the object. I'm looking for it. I know the change in temperature, final minus the initial. Final minus the initial. The final temperature is 30, the initial is 20. So 30 minus 20. I'm sorry, the 30 minus, was the initial for that, what was it, 20? What was the initial temperature for that bowl? We said it's going to be roughly about 90 degrees, we said, right? Because boiling is 100. By the time I take it out in the spoon and move it around and drop it there, it's probably 90 degrees. So the final minus the initial. So the initial temperature for that bowl is 90 degrees. Coming out of a different container. It wasn't here yet. It was right here. I'm going to put it there. Notice that number is negative. That's why Q lost is a negative value. Now let's see the gain one. The aluminum has a mass of what? 0.2. C for aluminum, which is what? 900. Change in temperature. Final minus the initial. The final is what? 30. Initial was 20. And let's look at the water. The mass of the water, which is what? 0.3. C for water, which is 4,186. And the final minus the initial, 30 minus 20. This is negative 60, right? Times 0.1, negative 6C. 30 minus 20 is 10. 10 times 0.2, that's a 2. Times 900, that's 1,800. This will be 3 times 4,186. 3 times 4,186. 12558. 14358 equals 6C. Can I get what specific heat for that? It is 2393. So then I look at my chart, I say, what is the closest number to 2393? Close one, probably ice there. 2393 is ice. I made up these numbers. I mean, we're not going to make up the numbers. We're going to actually do it. But you look at the chart, which one's the closest to my C, and that's what you have there. That's what our experiment's going to be. Okay. Now, we do have a list probably on the computer. If I type in specific heat, I have a bigger list than the list I have here.